Hello, my name is David Fehr, and I'm from the Flatey Group at the University of Iowa in the US. And today I'd like to talk to you about our theory of optically detected magnetic resonance of the silicon vacancy in silicon carbide and how it can sense magnetic fields optically. And we acknowledge these funding support. So the silicon vacancy um, consists of a ground and excited state that sits within the band gap of silicon carbide. And each of these states are actually quartet spin states. We have, plus three halves, plus one half, minus one half, minus three halves spin states. And each of these spin manifolds are separated by about 1.4 eV. And there's also this zero field splitting of the ground and excited manifolds on the order of micro eV. And so this is what the energy level diagram looks like at zero magnetic field. And in ODMR, we can optically excite the system um, with with light. Nothing special about it except it has the right energy. And sometime later, the system will relax back down to the ground state and emit a photon. And these photons are actually what we see on the detector. But the system can also relax back to the ground state from the excited state through a metastable state. And this does not necessarily conserve the spin, whereas absorption and spontaneous emission do. And these are non-radiative, so they do not. Uh, the system does not emit a photon when it relaxes through this pathway. And now, when you turn on a static magnetic field along the c-axis of the vacancy, these spin states begin to be split by the Zeeman energy. And when you turn on a microwave magnetic field, then you can cause coherent transitions between spin states. And so this causes there to be a characteristic uh, ODMR curve for each defect, and this is what the ODMR curve looks like as a function of Zeeman magnetic field on the right here. So each of these peaks or dips corresponds to a resonance condition being met. And so say for one of these peaks, we have a resonance condition um, like this, and un, un, in the presence of an unknown magnetic field, this characteristic curve gets shifted linearly by basically by the amount of the unknown magnetic field, and that's basically how the silicon vacancy can sense magnetic fields. All right, so just to skip to the results. So in blue is the measurement from our collaborators, and in red is our calculation. And it's a little bit hard to see in this picture, but there's a very nice agreement. And so yeah, so next we'll zoom in and we'll look at that. And right, so this is at a microwave frequency of 9.4 gigahertz, and we're able to extract the strength of the microwave magnetic field and also its electric field component, and also able to extract ground and excited manifold lifetimes. So we calculate ODMR using Lindblad master equations. So this is the steady state master equation. This first term is basically the Schrodinger equation, which governs the coherent evolution and dictates where the peaks and dips are going to be. This second term accounts for all the absorption, emission, and non-radiative transitions. And it's important to note that this first term it actually acts as a population generator, which will be important in a little bit. And the second term is a population dissipator. Our Hamiltonian looks like this for each spin manifold. So there's an axial zero field splitting. There's this is the Zeeman term, and we also have the microwave magnetic field, which is causing the transitions. And we also have the microwave electric field, which also causes some transitions. And we define the PL in the lower left, the photoluminescence in the lower left here, as the trace of the population generators that are associated with spontaneous emission, because it's those photons that we're seeing on the detector, is those generated by spontaneous emission. And on the right, this is actually what we're plotting. So it's the difference in PL with the microwave magnetic field turned off, and subtracting and dividing out the PL with the microwave turned off. So if we zoom into the larger features, this is what we see. And so we're able to, and so in blue is the data, and in red is our calculation. And we're able to extract the zero field splitting and the G factor using our calculations, which agrees with the literature. And we were actually able to see that these outer peaks are mainly broadened by the microwave power, whereas the inner peaks, we believe, are actually going to be broadened by hyperfine interactions. That's more of a hypothesis, but we're actually seeing that in current research right now. And if we zoom in on some other peaks, these are the half field resonances. And so in blue is the data, and red is the calculation. And what we're able to see is that, this discrepancy in broadening is actually due to um, some misalignment of the equipment, and also this shift is due to some uncertainty in the magnetic field source. And we're able to extract some parameters directly from this. So to conclude this, our data fits the model very well, and we're able to get a lot of information out of a simple ODMR experiment with our model. Um, and lastly, we want to know, can we get even more information from this ODMR data, such as the hyperfine couplings or coherence times? And so these are the types of things that we're actually investigating right now. So thank you for watching.